Welcome to Create Conway's Game of Life with Python. My name is Christopher, and I will be your guide. In this course, you will learn about cellular automaton, Conway's Game of Life, game loops, curses, and command line scripting. The code in this course was tested using Python 3.12. There's nothing here particularly modern, though pretty much any Python 3 should work. This is a Build It course. Rather than teach a specific concept, it incrementally walks you through the steps to create an application. And that application is Conway's Game of Life. Whether you've heard the name or not before, you've probably seen it or something inspired by it. Conway's Game of Life is more a simulation than a game. It consists of an animated grid with marked locations. Each frame in the animation is based on the previous frame, with state rules applied based on the currently marked locations. I'll walk you through a few different ideas about how to store the data for the game, then show you how to use the curses library to create text-based animations on the terminal. Once the basic simulation is running, I'll add features like command line arguments and the use of a PyProject TOML file so you can run the program without having to type Python on the command line. Insert your own joke about 42 here. Actually, this is a Python course. It should be an oblique reference to machines that go ping or the Galaxy song instead. In the previous lesson, I gave an overview of the course. In this lesson, I'll introduce you to cellular automata and Conway's specific rules to implement one. Conway's Game of Life isn't so much a game as a simulation. It is one type of cellular automata, which is a kind of visual math puzzle that has a regular grid of cells where each cell has a finite number of states, and the system is based on rules using the current state to produce the next state in the system. You can think of it as a graphical representation of a bunch of interlocking state machines, all operating at once. Conway's Game of Life is named after John Horton Conway, a British mathematician who in 1970 devised a specific set of rules. His version of the game uses a 2D grid of squares. Some more complex cellular automata use hexes or even go into the third dimension. In Conway's version, each square in his grid has only two states, usually referred to as alive or dead. And there are just a few simple rules for determining the next state, all of which are based on the immediate neighbors in the grid. Let's walk through the set of rules. Each of these gets applied to the current state or frame to determine the next state. For any given cell, if it is alive and less than two of its neighbors are alive, it dies. This is sometimes called the underpopulation rule. If it is alive and more than three of its neighbors are alive, it dies, sometimes called the overpopulation rule. If a cell is alive and exactly two or three of its neighbors is alive, it stays alive. And finally, if a cell is dead and exactly three of its neighbors is alive, the dead cell becomes alive. This is sometimes called the reproduction rule. Let's walk through the content of frame 1 and build up frame 2 by applying these four rules. Consider the cell with the question mark in the two frames. This is the first cell I'm going to process. Using the rules on the left to populate the cell in frame 2, based on the neighbors of the cell in frame 1. In frame 1, I've colored the neighbors of the question mark. Green indicates the three neighbors in the grid, while the other neighbors are outside the grid's boundaries. You can think of this in two different ways. Either as the grid being infinite, but only those items being displayed get processed, or you can think of it as bound and treat out-of-bound cells as dead. Every time I determine the future state of a cell, I consider 8 neighbors. In this case, 5 of which are outside the boundary. None of these 8 cells is currently alive, so the first rule applies. Less than 2 are alive, so the future state of the cell is dead, the same as its current state. I've moved a little further along, once again looking at the question mark cells. The blue shaded cells in frame 2 indicate cells that have already been processed. It's not really important as you can process the cells in any order, but I figured I'd give you a little visualization. Note that you're not doing in-cell editing. The entire future state is based on the entire current state. You don't change values in the same grid as you go. There is a variation on the game that does this, but it doesn't cause the same results. Like with the previous question mark case, the green in the left-hand side indicates the neighbors of the cell being computed. This cell has one alive neighbor. Note that the cell itself is not considered a neighbor. Once again, the first rule is getting applied, and the future state of this cell is dead. So in frame 2, the state is different than the current state. I've processed a few more cells, once again looking at the question marks. This time, there are 3 neighbors inside the green cells. The current cell is dead, and it has exactly 3 neighbors, so Rule 4 gets invoked. This cell gets it on, triggering the reproduction rule, and the future state is alive. Moving one cell to the right, the center cell is alive and has exactly 2 neighbors, so the third rule is run, leaving the cell alive. And this is the final state of the second frame. Calculating frame 3 would be done in the same way, but by using frame 2 as the current state. In the next lesson, I'll be talking about how to store this data for your program. File that away for now and maybe think about how you'd approach the problem yourself. One of the things mathematicians find so fascinating about cellular automata is how a few simple rules can create quite complex behavior. Conway's game of life is popular partially because the rules are so simple. Using the same 4 rules, but different starting patterns, produces drastically different outcomes. The example I used to show you how the rules work is known as the blinker pattern. It's part of a family of patterns known as oscillators, named that way because they loop endlessly through a series of frames. Our vertical bar becomes a horizontal one in the next frame, and in the following frame goes back to being vertical. There is a whole vocabulary behind patterns in cellular automata. There are blobs that do nothing. No matter how many frames go by, they retain the same shape. These are known as still life. I already showed you the blinker, but there are other types of oscillators as well. One goes through 15 different frames before repeating and is known as pentadecathlon. Another family of patterns are known as spaceships. These are oscillating patterns that move, so instead of oscillating in place, they shift along as the pattern changes. Our implementation of the game uses a pattern file so you can easily load in new patterns to play with without modifying the code. You've seen how the game of life works. Let's briefly think about what it will mean to implement it in Python. You're going to need to represent the state of the grid as data. You'll need some way of generating the next state based on the current one, and some patterns to use as the initial state. Those requirements apply to any implementation of cellular automata. Let's drill down onto some specifics for our program. The whole point of visualizing multiple frames is to animate it, so you'll need a way of displaying the next frame subsequently over the current one. Having initial patterns as part of the code is limiting, so let's use a data file so the user can insert their own patterns. The program is going to have some patterns that the user might want to muck with. At bare minimum, you're going to need the name of the initial pattern to use. But you might also want to change the size of the grid, how many frames to show, how fast the frames go, and other things. You can use command line arguments to change the parameters to your code. For most programs in your terminal, you run them directly. For Python code, you usually have to type Python, then the name of the script. There is a way to make your script more like a direct program though, so let's make it runnable. Of course, it is still Python, so all this needs to be done in a virtual environment. Here's the file structure I'm going to use as I go along. I'm calling the script rplife, rp for real Python. Inside the program's directory, I have a PyProject toml file that gets used to specify how the script gets built and ultimately will be how the script becomes a directly runnable program. There's a nested rplife directory inside my rplife directory. As annoying as I find this, it's common practice. The first level is the name of the package that gets installed, while the second level is the name of the Python module, and in our case, also the name of the runnable script hook. The dunder main file is the entry point for the script once it becomes runnable. CLI.py is where I'm going to put command line argument configuration. Grid.py stores the data grid. Patterns.py contains the definitions of the data structure for the initial patterns, and views.py is responsible for displaying content to the screen. This module also contains a data file, patterns.toml. This has some predefined patterns the user can get started with. You can create all these files in your IDE right now, leaving them empty if you like, or you can code the pieces as you go along. Don't forget that source code is provided with this course and available in the supporting material dropdown below the video. For this course, the code is divided into lesson directories. You can see the desired state at the end of each lesson as the course progresses. You're probably itching to write some code, but before getting there, I'm going to spend some time thinking about how to represent the data first. In the previous lesson, I showed you the rules to Conway's game of life. In this lesson, I'll spend some time talking about different ways of representing the simulation's data and how the algorithm works. Except with the simplest programs, there's almost always more than one way to approach a problem. In an earlier lesson, I hinted that one of the things to think about is how to represent the grid as data. My first thought with a grid of data is to store it as a list of lists. The blinker pattern would look like the code on the right here when using this format. Although this will work, consider what's involved in accessing the 8 neighbors for any cell. That's a lot of index calls. You could use some list slicing to optimize it a bit, but this still feels like a bit of a clunky approach. It's good from a storage standpoint, but not so good from our next frame algorithm. Instead, you could use a list of strings where each string represents a row, but you end up with the same index access problem, just referencing a character in the string instead of an item in a list. Memory-wise, this might be more compact as there's a bit more overhead to storing an integer than a character in a string, but it might also thrash more as strings are immutable, so when you modify a cell, you'd be replacing the entire string, meaning more garbage collecting going on. Python does have byte sequence data types, and you could use a list of bytes, with a bit being on or off for alive or dead. These are immutable, so you don't have the problem I mentioned with the string, and definitely would be more compact than a list of integers. With clever use of bit masks, you could calculate the sums rather quickly, but you're still having to access 3 rows to see all the neighbors for any given cells. You might have guessed by the tone in my voice that I'm not going with any of these choices. Instead, I'm going to use a set of tuples, where each tuple is the coordinates of the alive cells in the grid. Dead cells take up no space, and each alive cell translates into a single tuple. By storing the coordinates in a set, I can take advantage of set math when applying my logic to things currently alive or dead. I'll show you what that means in a bit. This kind of storage is sometimes referred to as sparse storage, as I'm only storing the bits of the grid with information rather than the entire grid. Sparse storage is the right approach if the majority of a grid system is empty, like it typically is with the game of life. Okay, so set of tuples with alive coordinates it is. What's that mean for figuring out the neighbors? Consider this grid with each cell labeled using a coordinate pair. To calculate the coordinates of the neighbor to the right of cell 2, 3, I add 1 to the column and nothing to the row. Applying that same logic, I can come up with a list of deltas to determine all the neighbors. To find all of a cell's neighbors, I add each of the 8 delta tuples in the column on the right to the cell's coordinates. That's accessing the neighbor. How about counting how many are alive? I'm going to come at this a bit backwards. First off, note that you only have to deal with cells that are currently alive. Only alive cells increase the count of a neighbor. And this is what I mean by backwards. Instead of looking at a cell and counting its neighbors, I'm going to look at a cell and use it to increment a count on its neighbors. Once I've processed the whole grid, I'll have a single number for each cell containing the count of alive neighbors. This hurts my brain a little. Let's look at an example. Starting with a blinker pattern with 3 alive cells. Again, only processing the alive cells. The green cells are the neighbors to the cell I'm currently processing. All the green cells get an initial count of 1 neighbor, as my current alive cell increments their neighbor count. I then move to the second alive cell and repeat. The green cells this time are this heart's neighbors, and they all get incremented. Those values that were 1 in the previous iteration now become 2. Finally, I move to the third heart and repeat the process. Like I said, backwards hurts my brain, but if you pick any cell and count the alive neighbors around it, you'll find this has worked. Taking this approach means you can store all of the neighbor counts in a dictionary, where the key is the coordinates of the cell and the value is the number of neighbors. Again, this is sparse. Cells without neighbors won't have a value in the dictionary. A handy tool for building this kind of dictionary is the default dict in the collections module. This kind of dictionary provides a default value for a key if the key is new. By making the default an integer, you can access a key and add 1 to it. If there was no key there before, you'll get 0 plus 1. If the key existed before, you'll get the current value plus 1. This saves a bunch of if-then-else clauses checking if the key exists. With the neighbor counts in place, it's time to use them to implement the rules. Let's start with those cells that are alive and have 2 or 3 neighbors. They're the ones that stay alive. On the left, I've highlighted the cells that have 2 or 3 neighbors using the color blue. In the middle, I have the set of currently alive cells. Because I'm storing these as sets, I can do set math on them, doing an AND operation. Any cell that is blue on the left and blue in the middle is staying alive in the final frame, which in this case is just the center heart. Of course, that only handles those cells that are staying alive. What about those that are coming alive? On the left, I have all the cells that have exactly 3 neighbors, once more highlighted in blue. Then in the middle, I have everything that is currently alive. As reproduction only happens for dead cells, I subtract the middle from the left to produce the 2 cells that are dead but coming alive. Finally, I take the results of the first and second calculations and union them together, giving the final result for the next frame. My blinker blinked. Although the approach taken here might not have been your first thought, it is particularly efficient, which is important if you start simulating large grids. Next up, I'll turn these concepts into actual code. In the previous lesson, I showed you how I'll be storing the game of life's data and how the next frame calculation is performed. In this lesson, I'll be turning those concepts into Python. Let's implement the basics and run some tests before getting all fancy with our presentation. To get going, you need a class to store the starting patterns and a class to store the grid. The grid class needs at least 2 methods, one to show the state of the grid for debugging, and one to calculate the next frame. Let me show you the code for both of these. I'm starting here with a class to store alive cells. It doubles as both the starting pattern and as the data inside the grid class, which I'll get to shortly. I'm using a data class, which if you haven't seen these before, they're a shortcut for creating a class with specific attributes. In this case, those attributes are name for the pattern and a set of tuples where the tuples are pairs of ints. Data classes use Python type hinting to specify what is to be stored in an attribute. The ability to use the built-in types like int and tuple as type hints was added in Python 3.9. If you're using something earlier, you'll have to import the corresponding type hint classes from the typing module instead. The next class here is the one that abstracts the grid. It stores the current frame as data and provides a method for calculating the next frame. At the top of the class, I have a couple of constants that get used when displaying the grid, showing a heart for alive and dot for dead. The constructor for the grid class takes a pattern, storing it. This object starts as the initial pattern and then gets modified as the frames progress. The evolve method is responsible for calculating the next state. Inside of it, I've got those 8 neighbor delta tuples used to find the nearest neighbors of a cell. You'll recall these values from the previous lesson. When I introduced the algorithm for counting neighbors, I mentioned that I'd use a default dict. By creating a default dict with an int, any key that doesn't exist will get created with an integer value. The default integer value is 0. Let me scroll down a little bit. This loop is what calculates the neighbor counts. Remember, this is being done the backwards way by looping through the alive cells. Then, for each cell, I loop through the neighbor deltas and increment the value in the neighbor counting dict. When the outer loop finishes, I'll have a dictionary where the keys are the coordinates of cells with neighbors, and the value is the number of neighbors that cell has. Here is where the set math begins. Comprehensions tend to be faster than their loop equivalents, but at the cost of readability. This is a set comprehension, denoted by the brace brackets. I've always found this a bit problematic personally, the fact that both set and dictionaries use the same symbols, but hey, no language is perfect. To read a comprehension like this, I tend to start in the middle and work my way outwards. The num neighbors dict is being iterated over. That's the middle part, and each iteration is returning a cell coordinate and a number. If that number is in the set containing 2 and 3, then the corresponding cell coordinate is put in the outer set. This corresponds to that first grid with blue cells I covered in the last lesson. I then take the newly calculated set containing cells with 2 or 3 neighbors and perform an AND operation on that and the currently alive cells. This gives me a set with the coordinates of cells that are staying alive. Staying alive. Really, did you not expect me to make that joke at some point? The next comprehension is for the reproduction sequence. This is similar to the previous one, but looking for those cells with exactly 3 neighbors. That comprehension should only apply to dead cells, so I subtract the live cells pattern. This leaves me with dead cells that have 3 neighbors. Those are the ones that come alive. And finally, I OR these 2 new sets together, storing it in the pattern object and giving me the next frame. Let me scroll down a bit more. Here, I'm implementing a dunder method to help debugging and make sure that everything is working. This method simply returns the name of the starter pattern and the current list of alive cells. Let's go to the REPL and try this puppy out. Importing the grid class, then the pattern, create a pattern, it's my blinker, and constructing a new grid passing that blinker pattern. If I print the grid, it shows the results of the dunder string method. As expected, it says it used the blinker pattern and has a list of the alive cells. You can kind of visualize the vertical bar. Calling evolve calculates the next frame, and you get the same name, but the alive cells have oscillated. I'll do it again. And you're back to the original because the blinker is an oscillator with a period of 2. It's a little hard to visualize the grid based on a list of cells, so let's go back and add some code. The asString method of the grid class is going to convert the alive cells list into a visual representation of the grid. It takes one argument, which is a tuple of the bounding area of the grid to display. Remember back at the beginning when I said you could think about the grid as infinite? Well, the boundaries can be thought of as just which part to display. Depending on what is sent in here, our alive cells might not even be visible. First, I expand the tuple out into start and end values for columns and rows. Then I build a title string based on the pattern name, but centered. Then I loop through the rows, constructing each, printing out a dot if the cell is not in the alive list, and a heart if it is. Remember the alive and dead constants at the top of the file, which were heart and dot respectively. All those cells get joined into a row, and each is joined with a carriage return. Let's go back to the REPL and visualize our grids. I'll show our blinker using a 5x5 the same way I've shown it in the slides. And there you go, all visualize-y. Let me get the next frame. And it blinked. You've got the basics of the game, and now have a way to visualize it all. Hard coding a starter pattern kind of sucks. Next up, let's try to suck a little less.